Good morning, everyone. Welcome to Automation Alley's virtual tech takeover. I'm Seta Sykes, Automation Alley's account manager. This tech takeover is brought to you by one of our foundation members, Manpower Group. Manpower Group provides administrative and supportive services, professional services, and business services through its four primary brands: Manpower, contingent staffing and permanent recruitment; Experts, professional resourcing and project-based solutions; Right Management, career management, workforce consulting and training and development; and Manpower Group Solutions, managed services and outsourcing. If you have any questions regarding Manpower or any of their services, I'll be more than happy to connect you with a representative. Information can also be found on the Tech Takeover information page. And keep in mind, every Wednesday, or most Wednesdays, we host these member-led Industry 4.0 focus sessions via live stream. This week's topic is using virtual engineering simulation to accelerate product development. I'm pleased to be joined today by our speaker, Ali, Application Engineering Manager from Ansys. We'll be doing a Q&A at the end of today's discussion or presentation. So please use the Q&A function at the bottom of your screen to ask questions. Thank you. And I'd like to thank Ali as well, and welcome Ali, and you may begin.
Thank you very much. Good morning, everyone. I hope that everyone can see my screen. It's a pleasure to be here, and I wanted to thank Automation Alley for this opportunity. And this is actually the presentation that I'm going through has a direct relationship with Industrial 4.0 in terms of enablement of this technology. So here is the outline of my talk. I'm going to basically briefly give an overview of the process and the tools as it relates to virtual engineering and design, and talk about the collaboration aspect and this multidisciplinary design and analysis approaches. And basically, I'm going to present this story through an example of a multidisciplinary structural optimization where we are focusing on an automotive, let's say, subsystem or subassembly, looking at different attributes such as durability, safety, and NVH, and kind of discuss how this basically design process comes together to kind of meet these different needs in terms of the life, safety, and noise. So to start with, it's basically, I wanted to briefly talk about the fact that simulation technology and virtual engineering in general has come a very long way. And I mean, previously we were quite basically focusing on the structural aspect or fluid dynamics aspect or electromagnetic aspects to kind of answer a question related to design or validate the design or figure out what the failure associated with the design is. But these days, just because of the value of the virtual engineering and simulation technology in general, people are trying to get the most out of this type of, let's say, analysis. That basically is a main driver for enhancing the fidelity of these models to represent more accurate physics and one side. And the other side, we are living in a world that, for example, air is interacting with the structure, and that basically means that it basically adds a pressure into the structure, and we want to account for the accurate transfer of, let's say, one physics, in this case, fluid dynamics, into structure. And in order to that, we are kind of needing to couple two different tools or two different physics together, right? So this is there is a layer of complexity in the simulation itself. On the other hand, because there are many players and there are many experts working in these different domains, we need to have a very effective project management and data transfer between these different disciplines, right? We need to have a way to kind of leverage our legacy data from previous, let's say, designs. And at the same time, we need to have a kind of give a visibility, for example, to chief engineers on the progress that we are making in the virtual, basically, design process steps, right? So all of these requires a more collaborative type of activities or a platform or ecosystem that allows you to kind of be able to put all of these things together. And one important thing to remember when we are looking at these different attributes from, let's say, different types of disciplines, we're dealing with a so-called multi-objective criteria to meet. And that basically is a main driver for us to have and look into optimization in general, right? So that basically, this process is very complex. So, I mean, having it in a PC, working by your own and kind of doing the file management and making sure that the file has a proper name or proper date and these types of things is a stretch. It's really difficult to accomplish that. Plus the fact that, I mean, with this huge drive towards cloud and cloud computing, you want to have a different layer. You want to have this visibility in cloud and in a public or private cloud. In addition to that, we know that all of these basically simulation information are actually there are a lot of different information that you need for your simulation, which are coming from different sources. For example, you have the PLM that manages the CAD data, and you wanna have this automatically connected to this virtual system. At the same time, you have a lot of information that might be related to materials, test data, and previous analysis, and so on and so forth. So there are a lot of basically different sources and formats that are going to contribute to this, the complexity of this process. So just to summarize, there is complexity and the management of this multidisciplinary, let's say, users and even multi-geographic type of activity. And there is a complexity in decision-making because we might have competing, let's say, criteria to meet. And then we have, obviously, as you see here, we have complexity in handling data and maintaining traceability of data. So this is, I'm going to kind of briefly touch upon these different aspects through an example. And at the same time, obviously, we need to have a system that kind of allows you to do searching, effective searching to enhance the productivity of the product. At the same time, when we are looking at the realistic, let's say, engineering organizations, there are a lot of different tools that are available, and there is no single basically provider that has all of these tools. So you need to have this basically principle of interoperability built into this ecosystem so that people are not limited to one vendor type of basically tools. And they also want to, and basically they want to have the better organization and orchestration of the process and data. So this is really a journey, building this efficient digital ecosystem or digital thread, which basically connects your CAE and materials and PLM and requirements all together. It's a digital, basically thread, we call it, which is the main enabler for digital twin and industrial 4.0 from a virtual engineering simulation perspective. So again, like I said, this is a long journey, and people are kind of depending on the needs of the customer. People are spending time on basically streamlining some of these processes. You cannot accomplish this in one day, obviously, as all of us know. So let's actually take a quick look at a project that basically involves, as I mentioned, in durability and estimating the fatigue life of the structure, noise and vibration and safety. And you want to basically meet a certain criteria that basically, or come up with a design that meets all of these different criteria together, right? So in terms of, let's talk about just the project management. You have different, let's say, subject matter experts are deriving these different, let's call them swim lanes. And then they need to kind of exchange information and make sure that their process or their design is up to date and everyone is using the same, basically, final design, right? So this is a very lengthy process. So what we are trying to basically answer is, how do we archive data? How to maintain the traceability? What the status? What is the status of this project? I mean, remember, these team members could be anywhere in the world, right? So it's a complex process. So let's just spend a little bit of a time talking about this example, as I mentioned, which is only focused on 3 fundamental disciplines on the structural mechanics. I mean, this is just an example. It could be anything. It could involve electromagnetic system, software development, control development, and so forth. But just for the sake of time and relevancy, let's just take a quick look at this example, right? So we have a, let's say, front end or bumper system, bumper rail type of structure that we have in the car, and we need to meet certain criteria for each of these domains. How do we accomplish that? We want to accomplish that through virtual engineering and simulation technology, right? And again, we have to meet, there are so-called constraints built in all of these things. So you cannot have a, for example, less durable structure. You have to maintain a certain, let's say, number of cycles that this structure will withstand. At the same time, it should not basically have a structure-borne noise, and it has to be safe. It has to protect occupants during crash scenario. And again, we want to look into these things together, and that's why we need to look into multidisciplinary design optimization. So what happens, just to simplify things, is that we have a project manager, right, who assigns this project to these multiple, let's say, subject matter experts. Each of these experts, they need to communicate, get the information, and start basically doing their job, and kind of come up with the series of solutions as it relates to all of these things, right? So at this level, I mean, sometimes people are going to kind of have, let's say, calibration meeting to kind of make sure that they're using similar type of, let's say, geometry or information and design. And I mean, this is kind of, it's difficult because it's not necessarily digitized, right? And then, so the main question is, okay, how I can maybe come up with a solution that kind of addresses these competing criteria together, right? And this is the main motivation behind this MDO engineer, to kind of integrate these different solutions together, and then let's say, process integration and design optimization to orchestrate these different, let's say, models and come up with a final design. And then obviously we need to kind of do the design validation and design review, and then do the final report. And that basically is an ideal scenario in a digital, in a very simple, let's say, a schematic way of how we are executing here. So in order for doing this, we need to have our, let's call it, durability engine, NVH, or dynamic engine, and safety engine first developed individually. So we need to go deeper into this one, and I'm gonna actually go deeper into, for example, durability and NVH and safety, and talk a little bit about how these people are kind of being able to automate and streamline this process. And in order for that, we are using Ansys Workbench, which is our platform for multidisciplinary analysis, right? So this is what you see on the screen is a schematic of a Workbench project, which you can actually easily get an idea of what is going on. Usually you start with some engineering information. Those engineering information could be your CAD model, could be your material, it could be some loads that are coming from different physics, different tools and so forth. And then we have this model assembly steps, which allows you to, for example, mix and match, let's say, different CAD models, which might come from different sources, or mix and match a CAD model with an existing, let's say, finite element design. And then you might want to do a validation and then analysis. So with this Workbench framework and basically connecting these different, let's say, modules together, what we are really trying to accomplish is we want to spend less time on setting up the engineering, let's say, the computational aspect, and spend more time on decision making and the physics aspect and the engineering aspect, which is really the main value of simulation. Because many times actually people spend time on, for example, meshing, on making sure that quality is good and so forth. But the main thing is what Workbench is doing here is it's basically, it is built based on this principle of persistency and associativity, which allows these information that you have defined, for example, in your loading and boundary condition and so forth, remains persistent even if you change the geometry or even if you go through the change in geometry. And that way, we are basically increasing and streamlining the engineering decision-making efficiency, right? And you don't need to spend more time redoing whatever you did from a numerical perspective. Just taking a quick look at the dynamic and NVH aspect. What you see here is a very simplified workflow that an NVH subject matter expert has put together to address the dynamic, basically, reaction of this bumper assembly system due to different loading conditions. These loading conditions are based on the best practices that each company has came up with. But the main thing is we are streamlining these steps. And again, based on that persistence and associativity design principle, which exists in Ansys Workbench, if we add or vary the geometry or change the material and so on and so forth, we don't need to be worried about, for example, the loading condition. It's a kind of a digital way of actually documenting best practices or documenting what is needed to be done in NVH workflow. So once you build this process once, the iteration will be easier. Not only that, actually, as you see here, you can couple this, you can parameterize the geometry, and then you can have an integrated way of an Excel sheet. So you can basically log in and get in here and just vary the design variables and get some responses. Those responses are something that we have to came up with. So for example, it's it could be, for example, maximum deformation, or it could be just the animation of how the structure behaves or responds to a certain load in a certain direction. Same story actually applies on the crash worthiness. In this case, we are using our LS-DYNA solver to solve this crash worthiness problem. Again, same thing applies here. There is a geometry and a material information needed here, and then the rest is basically the best practices that we need to have to address this type of crash worthiness problem. You want to basically maximize the energy absorption during the crash scenario while basically meeting the requirements as it relates to lightweight and fuel efficiency, right? So based on that, we define a response or a couple of multiple responses and the variables, and this basically process allows you to kind of automate the entire process together. Same story applies when we work on durability. Again, the physics, the best practices, the environmental condition could be different. It could be, we can account for heat transfer. We can account for different interaction of mechanical loads and so forth. We can, for example, account for the efficiency of this if we had, for example, a tow hook attached to this bumper system and so forth, right? And then again, there are multiple load cases. Someone might, we might need to, for example, address what happens if someone jumps on the bumper. Would that affect the fatigue life of this component and so forth, right? And again, here I just summarized the same thing that I mentioned in the previous slides. You have a series of inputs, could be dimensions, material, different types of loadings, and then you have series of responses, right? And based on this automated framework that we have established, or it's kind of a templatized design principle that exists in Workbench. So you can look into these different, let's say, combination of these design variables, which is different geometric dimensions, and kind of get some answers in the response. Obviously, when the problems becomes more complex, it's a little bit hard to find the best possible choice through just trial and error. This is the main motivation that you need to look into some type of mathematical optimization. Let's say you have hundreds of, let's say, design variables, so representing different dimensions in your geometry, as well as material and so forth. So the first step that you need to do is to do sensitivity analysis and find the most influential parameters that are going to influence your durability and crash and NVH, and that just focus and focus your attention to those most influential parameters, right? And then use mathematical optimization to give you the best possible answer. So in order to accomplish that, again, going back to my previous slide, you have safety, you have durability, and you have noise and vibration, right? And you have to put all of these things together. In order to address this problem, we have another tool called OptiSlang, which is allowing you to do PIDO, which stands for Process Integration and Design Optimization. So what you're doing is here is you are leveraging the same files or same information that each of those individual members, a subject matter expert, have come up with. So this box here, or this node here, represents an automated version of that Workbench project, which was developed for durability. The same thing for crash and the same thing for NVH. So it means that we have a series of parametric models, which is made up of inputs and responses. And we want to basically run these things together to make a decision to come up with the best possible design. As I mentioned, the first step to do a sensitivity study. And actually what you see here is basically a sequence of events that happens in the software automatically too. So the first thing is to find the most influential parameters, as I mentioned. And once you find that most influential parameter, the next step is to define your objective. Most of the time, the objective is minimizing the mass, and then looking to, while maintaining and respecting some constraints that are coming from the criteria associated with these different designs. So And basically, then you use the mathematical optimization methodology, which in here is actually kind of streamlined. It's built in. It will give you, based on the type of information that you have in your simulation data, it gives you a series of recommendations on what is needed to be done, what type of algorithm to use. And then you can basically look into the results. I'm just showing a very schematic view that, for example, you can, after doing a sensitivity analysis, we realize that, for example, these plate thickness and the box thickness are the main drivers to address and the parameters associated with the geometry of these, which is maybe over 10 parameters, are the most influential ones to kind of notice and consider. And using this technology and looking at our optimization, let's say formulation, which was the mass minimization to meet the fuel efficiency criteria while respecting constraints for durability and NVH and crashworthiness, we can come up with these, let's say, design curves or response surface models. And in the next stage of this design optimization process, we can basically work with these so-called response functions, response surfaces to find the best possible design. And obviously after that, we can do a lot of validations and so forth. So what we have covered so far was basically the technical aspect associated with durability, crash, and NVH, and how you can put all of these things together through a multidisciplinary design optimization approach, right? So the next question is, how can I streamline this? How can I make sure, and going back to my basically management slide or managing the simulation process slide, how can we streamline this process? I mean, remember, from a single analysis, we moved to a multiple analysis. We have done sensitivity analysis. So we have lots of information now collected because of the fact that we looked into different variations of design. Not only that, we added a multidisciplinary design optimization framework, which actually gave you ability to kind of look into even more design scenarios. And at the same time, going back to the previous discussion, each of these, let's say, swim lanes or disciplines could be located in different places. There are multiple users involved in these different aspects and so forth. So, I mean, just the project management aspect of it and making sure whether they are efficiently working and kind of exchanging information with one another is actually a very important thing. Not only that, as a project manager, right, or as a team member, you wanna have an access to, let's say, a tool, a web tool that allows you to kind of keep track of the project without really needing any level of familiarity with a specific tool. So you want to have those being exposed in a, let's say, web format. You want to kind of look into some of the design variations, for example, as a project manager or as an individual contributor, right? And at the same time, basically you want to have or maybe manage giving access or permission to these different team members depending on the policy of the company and so forth. And at the same time, you want to streamline the process of job submission to high performance computing. You may want to, and actually another important thing is you may want to maintain the traceability and see how did we go through the design variation? What made us, for example, change the geometry? How these different, let's say, files are kind of connected or associated with one another. And you want to graphically see what was going on when you started from the project to where you are today. So just going back to this simplified example that I mentioned. So the first thing is you have a project manager who is interested to create a project and assign it to different resources. So we have this web UI, which is, or this ecosystem or platform that we're using called Ansys Minerva. They initiate the project, they assign the reviewers and so forth, and then they basically can also attach some type of, let's say, document for people in terms of best practices. The files are connected to the PLM system or can be connected to the PLM system, so people can directly load those files from this project. So basically the project manager assigned multiple people to different tasks and also kicked off the project and also provided some information related to the sources of information. Now, the next step is to kind of being able to kind of come up with this Gantt chart and kind of see how the process is going on in terms of creating a geometry and design, which is a precursor to any type of analysis. And then once this basically geometry creation has been done, then multiple team members are going to go through their own processes in terms of durability, dynamics, and safety. And then our MDO engineer, multidisciplinary design optimization engineer, needs to put these three processes together and then perform the analysis and come up with the result and so forth. So this one gives a very nice visibility to a project manager to see what is going on, where we are, and what the dependencies are at the very early stage and actually at the beginning of the project. We can track the status of this process, who's doing what, which part of this project is complete, which one is doing, and so forth. So it gives a very nice overview to project manager on where things are and how people are contributing and helping with this, with basically getting this project to the end, the virtual engineering project. So this is, as I mentioned, this is a work order process, not only just a work order, simple work order process, but it allows you to kind of look into the status and the progress along the way. And actually you can get in and kind of look into these different things using these hyperlinks and see where we are in terms of crash tests or crash simulations and so forth, and see those results. And as I mentioned, you can also look into the revision tracking and kind of look into the variation of the design process as we go along. And because of the fact that you're documenting these things, you can see why, for example, a certain thickness or a certain dimension in a certain part of the structure has changed. And you can kind of see that. And not only that, you can also look into the traceability of data. Where did we start? What type of, let's say, Workbench templates or Ansys mechanical templates has been used, and how these things varied along the way. And this is, by the way, this is a pretty long chain of information. I just took a snapshot of a portion of it. So that's basically the whole story behind let's say, these sets of disruptive tools that need to work together. And they are in different layers. They're on the subject matter expert layer to enable the templatization and kind of documenting along the way type of activities that is available in Workbench. Then the other layer is the multidisciplinary analysis and optimization, where you really want to look into the engineering and the decision-making process to see where, for example, your design needs to get updated, and that update has to be meeting different criteria, which is driven by different disciplines. And in another layer, you're looking at basically the actual project management aspect and the file management aspect, and the fact that how these different steps are executed together, right? So, I mean, I gave a very simple example related to Ansys products, which was used in different physics, but that could be in subsystem level, in subassembly, or system level, or super system level, or systems of system level, right? So there is no limitation on this basically vision, but I mean, the tool chain might be different, the best practices might be different, the subject matter, the number of people, and so on and so forth. I mean, this tool, especially Ansys Minerva, remains agnostic, and actually Ansys OptiSlang as well, remain agnostic to their engines or the tools. And those types of, let's say, fast pre-processing that I just mentioned is available for not only Ansys products, but other products. And same thing, basically, this process can basically help you to automate the process and kind of avoid doing repeated things, which might be subjected to mistake and so forth, right? And also you can look into efficient algorithms as it relates to data analysis in general. For example, meta modeling and response surfaces, the type of mathematical and statistical method that exists in sensitivity analysis and optimization and robustness analysis and so forth. And then another layer, as we talked about, was basically simulation and process data management. And actually one important aspect of putting all of these stories together, it actually really helps with the knowledge transfer and knowledge exchange between team members. People have a kind of a visual perspective of what is going on. And it gives a different levels of exposure to people to really know how basically all the decisions come together to come out to meet a series of criteria. And not only that, you can reuse these models, because now it's not a matter of just going to your individual, let's say, PC to figure out what the latest version is, or in a shared folder, but you have a process and you can look into the traceability and so forth. So for example, if let's say a failure happens in the field and you want to go back and see and do the root cause analysis, it's much easier because you know where the latest and the greatest version is, what type of analysis has been done, whether we have done analysis to address that specific failure or not. That type of transparency will be there automatically when we use these types of tool sets. And in addition to that, I mean, talking about this Industrial 4.0, one of the major, let's say, pillars of Industrial 4.0 is ability to have digital twins. And actually, you need to build this digital thread to enable digital twin. So once you have the digital twin of your, let's say, design, then that digital twin could be used, that digital, let's say, virtual design could be used as a digital twin by connecting it to a real world data with the sensors and so forth. So it basically helps to accelerate the digital twin creation, which is very relevant and one of the center or pillars of Industrial 4.0. Again, this is a pretty complex problem to solve. And as we actually made our journey from single physics to multiple physics and then multidisciplinary design optimization, I mean, the message is, I mean, this has to be decided based on, let's say, the initiative and priorities in different customers. So this can be only focused on the physics. It could be focused on, in terms of adoption I'm talking about, it could be how to enable multidisciplinary design and analysis and optimization. And what are the criteria that each discipline or each single physics has to meet to to enable this MDO. And then, something that we didn't talk about, how you can connect this to material intelligence and have your basically testing information related to the material comes into picture. And obviously how this is going to be connected to the PLM system, which maintains the CAD geometry, and also maybe the requirement management system that allows you to kind of keep track of different requirements that we have in our design. And the bigger picture question is, okay, how we can effectively and efficiently manage these, basically the CAE process and so forth. So the main message here is, it's basically, this is a journey. We have customers that are kind of focusing on different aspects of this. I mean, some, they're a little bit ahead with this. Some they're focusing on some specific aspect. But in order for us to really see and realize the value of digital digitization and digital thread, and obviously digital twin, we believe that these sets of tools that address different levels of complexity at different levels of the process is going to be very helpful. So with this, I'm going to actually wrap up my presentation, and I would love to entertain your questions and comments. But before doing that, I just wanted to invite all of you to this virtual event. This is the second virtual event that we are holding at Ansys. It's going to be from April, basically April 20th and 21st. And there is a wealth of material and information related to all of these basically different aspects that I've talked about, from Ansys Minerva and how to manage the project, to multidisciplinary analysis and optimization and data analysis, or specific physics, not only the physics that I talked about, but electromagnetic, fluid dynamics, lighting, and many others. So you're more than welcome to join us, and I have the information here. So with this, I'm going to wrap it up and give it back to Cetis.
Thank you to our viewers today for watching. We hope that you tune in next week for our next Tech Takeover on March 17th about Project Diamond, a roadmap for forging customer success with Mark Forge. And just a reminder that this event and all of our Tech Takeovers are archived on our website for you to view later. Thanks, everyone, and have a great rest of your day.